Um, Determining asteroid diameters from occultations, which is what we've been doing for the last 30 years at one sort of level. Might take my glasses off, there's a bit of reflection there. First slide. I better make sure I can. Okay. Our asteroid occultation predictions, we rely on asteroid diameters which have been determined in a particular order. The primary source which is used in the behind the scenes is the Japanese satellite Akari AQA, asteroidal, one of the A's is for asteroidal, the other one is for Akari. They're infrared satellite measurements. On the basis of an infrared satellite measurement is they measure the reflectance at several infrared wavelengths, and from that they deduce the albedo of the asteroid, and then given the albedo and the magnitude of the asteroid, you can infer the diameter. The second in priority is IRAS. That's a relatively old NASA satellite. The DIAM-LB, diameter and albedo measurements, the infrared satellite measurements again. Then you've got WISE and NEO-WISE, the main belt asteroid measurements that come out of WISE. And finally, a very crude measurement, we use the asteroid absolute magnitude H0 and a nominal albedo, and we derive the diameter as 10 raised to the power of 3.52 minus H0 on 5. Next slide. Here we go. Now, a month or two back, there was an article in the New York Times. It was an article, the author, I forget the person's name. It's a fairly wealthy person that used to work for Microsoft, has a bit of a reputation for stirring the pot and creating a bit of controversy, and he has a bit of a scientific background. And he asserted that the NASA scientists responsible for analysing the WISE and NEO-WISE data weren't analysing the data correctly, and in some cases their diameter determinations could be hugely out, not just a few kilometres, but 50% out, large differences. The arguments that he raised were based on theoretical considerations of the mathematics and statistics used. He's put together a paper which is on ArchiveX. It's well over 100 pages of fairly dense, repetitive mathematics and stuff, and very heavy reading. And as I said, he concluded that the WISE and NEO-WISE diameters could be in errors by large amounts. His own focus was only on WISE and NEO-WISE, and I guess it's the JPL scientists behind that. He didn't seem to be taking the same attack with Acua and Iris, but I guess that was implicit in what some of it was he did. Anyway, all of that highlighted a particular problem of, we have these asteroid diameters measured by the satellites, but how do we actually check the validity of those satellite determinations, given they're based on reflectance parameters and not an actual measurement of the size of the asteroid? It's not a matter of measuring the angular diameter and saying it's 10.7 milliarc seconds across, therefore its diameter is so much. it's measured on, it's based on infrared reflectance. Next slide. So how do we currently go about measuring the size of an asteroid? Now, I hope I'm reasonably complete in this. The first and most precise method is a direct measure from a visiting satellite, and there's that satellite that's visited is it Vesta and Ceres. I forget what the name of that is there, but there aren't many asteroids which have been visited by a satellite, the Dawn satellite. Then there's radar imaging, where you send off radar signals and get the reflectance. There's not many of those, and mainly of near-Earth asteroids, so you've got a bounce signal strong enough to detect it. And you need a pretty decent signal to come back because you're looking for the spatial pattern that comes back in the signal. Then you can do direct imaging with adaptive optics. Need a large telescope and right circumstances, and there aren't many of those done. And then the final technique is occultations, which is what we do. Next slide. Okay, occultations. Is it straightforward? Well, no. As we all know all too well, asteroids are irregular in shape. They're not nice, smooth balls like a soccer ball. An asteroidal occultation can derive a profile for a particular orientation of an asteroid at the 1 kilometre level. I think our normal main belt asteroidal occultation observations, we are generally working to a precision which is close to about 1 kilometre or a mile, that type of accuracy. It's not 10 or 100 miles, and it's not hundreds of metres, it's about 1 kilometre. The fundamental problem that we have is, how do you derive the mean diameter of an asteroid from a single observed profile? You've got no knowledge about what the shape of the asteroid is. So you see a profile, you can measure that profile, but how does that measured profile relate to the overall size of the asteroid? And then of course we get multiple observations from an asteroid, and I think probably most people have had experiences with that and seen that, but how do you combine the irregular profile you get from one occultation with an irregular profile of the same asteroid obtained at another occultation and make any sense out of it? It's a serious problem. Next slide. Now, at this stage, there's an interesting issue surfaces in this discussion. When we talk about diameters of asteroids, the usual terminology used is we refer to the mean diameter of an asteroid. And in broad terms, that's intended to say, well, we've got this irregular shaped asteroid, but in some form of average, its diameter is this much. But what actually is the meaning of a mean diameter? The one meaning, and I think the most logical meaning, is it's the diameter of a sphere that has the same volume as the object. That's effectively what you get if you integrate the radius vector of the surface of the asteroid over the volume of the asteroid. It's the sphere that has the same volume. But when you start looking at the infrared satellite measurements, where they're looking at the reflectance from the surface of the asteroid, that raises the question of whether those measurements effectively reduce to the diameter of a sphere that has the same surface area as the object, as the asteroid. And there's a further possibility, which is in fact used in some areas of investigation apparently, of a triaxial ellipsoid that has the same volume and moment of inertia as the object. But of course, as a triaxial ellipsoid, to have a single diameter, a mean diameter, is a bit of a meaningless statement. Next slide. Now, it's interesting, you might say, well, what's the difference between these different mean diameters? Interestingly, the diameter of spheres of equal volume and equal surface area of an irregular asteroid are generally different. And for those that want to do something easily with pen and paper, you can work out the difference of the mean diameter of a cube, a simple cube, based on equivalence of surface area and equivalence of volume. And you find that the mean diameter based on surface area of a cube is about 11% larger than the mean diameter based on the volume of the cube. So it's an important issue. Now, as indicated earlier, the most logical basis in my view is volume equivalence, and that's the basis which the Dammit shape models are built on. From discussions I've had with some people involved with NEOWISE, their determinations are effectively based on surface equivalence. And I suspect that's probably the case for IRAS and AQA. And you've got the problem that with some of these satellite measurements, they're using ellipsoidal determinations, and then you don't have a single diameter. When we're looking at doing diameters, trying to drive diameters at the 1 kilometre level, 11% variation potentially on something, say 100 kilometres diameter, that's 10 kilometres difference. The type of precision that we are capable of achieving, it's actually important that we are clear about what the basis of the mean diameter is that we are reporting. It's a fundamental issue, and I'm going to be proceeding on the basis that we're going to be working on volume equivalence, not surface area equivalence. Next slide. Using shape models. Let me just, I've got another, because I've various things, I've got to have another laptop here showing the presentation so I can read a bit ahead. Now, we can solve the occultation profile issue of, hey, we've got a single profile, how do we get the diameter? By fitting our occultation observations to shape models. Now, shape models are determined by mainly amateur observations. It's a photoelectric type pursuit that amateurs around the world get involved with, of measuring accurate light curves of the asteroids at different parts of their orbit at a relatively high level of precision, and then a complex mathematical inversion process where they derive the axis of rotation of the asteroid and derive a shape model to represent the light curves. Very complex process. I don't pretend to understand it, but it works. The main source of shape models is the system called DAMIT, Dynamic Asteroid. I won't try to remember what DAMIT actually stands for. It now, and I've had discussions with the people behind that, and their shape models now include in the metadata which comes down with the shape model the dimensions of the mean diameter based on both volume and surface with each shape model. And if you have more than one shape model for an asteroid, the interesting thing is that the mean diameters of those shape models, as a general proposition, is different for each displayed shape model, even though it's the same asteroid. Given the dimension of the mean diameter used to plot the shape model, if we fit our occultation chords to the shape model, the occultation chords give a very specific dimension in kilometres onto the shape model, and that gives you directly the dimension of the mean diameter used to draw the shape model. So by fitting our chords from a single occultation event to a shape model, we can directly measure the asteroid's mean diameter within the precision of the shape model. Next slide. However, like all things where you have a problem and a solution surfaces and you think, we have the solution, all our problems are solved, well, relative life is, well, that's usually the start of a new set of problems and issues. And using shape models have a range of issues which we actually have to address. The first issue, the shape models are derived from light curves measured over a period of years. They have to cover different parts of the orbit. So typical orbit 3 or 4 years. So you've got shape light curve measurements over that type of period, frequently over more than one orbit of the asteroid, and they've all got to be brought together. And the light curve variations, it's not like a short eclipsing binary system. You tend to have broad variations for most asteroids. That means that when you analyse the light curves, you have a period of rotation. It's got a level of uncertainty that unfortunately, is not readily available. In the data I've been able to find, I haven't seen any figures where they say the period is 0.00356 whatever hours plus or minus some value. The plus or minus value is never quoted, which is unfortunate. In practical terms, the practical uncertainty that we need to deal with is what is the uncertainty in the orientation of the model at the time of our current occultation. Now that uncertainty is governed by two factors. The first one is the length of time covered by the light curves used to derive the shape models, whether that was over 5 years or 20 years, for example. And the second element is the elapsed time since the end of the light curve coverage. And for some of the light curves, particularly of the lower numbered asteroids, that could be well over 20 years. The net result is that the uncertainty in the date of an occultation can vary between a small fraction of a rotation, to multiple rotations of the asteroid, which is a bit of a problem. But what that leads to is that, as a general proposition, unless the light curve and the shape model has been very recently published, the asteroid shape model plotted for the time of an event will be incorrectly oriented because of the uncertainty in the rotation period. So whilst on the previous presentation we saw some asteroid shape models plotted against some occultations, we see that? I'm getting confused here. Well, we can do that. The alignment of the shape models with the occultation results is often a matter of good chance rather than good planning. Next slide. The second practical problem. The light curve inversion process for determining the shape model almost always has multiple solutions. And the multiple solutions arise from different orientations of the axis of rotation, and these orientations are derived out of the analysis of the light curves. The light curve, the shape model derivation process almost inevitably comes up with more than one shape model. There's, from my reading of the lists, there's only about 10% of asteroids with shape models have just one shape model. Most of them have two, and that's mainly because DAMIT only supports two. In the ISAM system, which doesn't have as many asteroids covered with shape models, they have asteroids with up to 4 shape models in that system. And interestingly, on some of those shape models, all the DAMIT shape models are in ISAM, but some of the models in ISAM aren't in DAMIT. And I've seen a couple of events where one of the ISAM models, which is not in DAMIT, would appear to be the correct shape model. So the practical problem is potentially multiple shape model solutions, and we need to figure out which one is in fact the correct one. Next slide. So our challenge: to reliably determine the mean diameter using occultations, we need to use shape models. But first of all, we've got to identify which shape model is the correct model, and then derive a period of rotation that gives the correct orientation of that shape model for plural occultation events. And that's an important bit. We can't reliably use this process if we only have one occultation result, because, as we'll see a bit later on, there's some other issues in there. But if we can match our occultation results under these circumstances, we can determine the mean diameter by just fitting our occultation results to the shape model. And if we do this for multiple events, we finish up with a statistical measurement from the multiple events. Next slide. So, what do we have? In occult, and some of what I'm talking about is going to be in the next version, which will come out hopefully next week, when an issue with ISAM and has been fixed up. Occult now has a tool to facilitate the fitting of occultation cords to shape models. It allows the download of multiple orientations of a shape model at different intervals, and selectively different intervals, so that you can find the best fit and identify the correct model without having to spend too much time manually identifying fistfuls of models. And it also allows the download of a range of information relating to the basis of the light curve. So you can download, a simple download gives you the dates covered by each of the light curves used to generate the light curve, the shape model. So you can see how long the observation span to create the shape model and how long it's been since the last observations used to make the shape model. And this gives you a basis to assess the reliability of the orientation for today's date. Next slide. Now this is an image of the shape model page, which is now in Occult. I've brought together both the DAMIT and ISAM shape models. The top line of this, I won't go into this in too much detail. The top line gives up to 4 DAMIT shape models. The bottom line, top center, gives 4 ISAM models. It says failed there. ISAM has a problem at the moment. There's a web indexing service out of China which is generating 1,000 requests per minute for shape models, and it's flooding the system. And the owner's on holidays in Italy. He'll be back sometime in the next 24 hours at home to get that out of his system. And then ISAM will be able to assist in this. And ISAM's got an advantage that they generate shape models faster than the DAMIT system does. You've got a list of asteroids and shape models at the left, and you can change the plot size at the top right, and you can change the relative size of the ISAM and DAMIT plots. There's some technical stuff around there. Let's move on to the next slide. Options for shape model downloads. Let me when you click with model image, you've got options to display the mean radius on the image. If you're accessing the ISAM system, there's an option where you can see the rotational axis, and that can be very useful to get a sense of how the asteroid is rotating on the screen. And then you've got 4 download options, which each option downloads 10 shape models. First one, it's got a phase adjustment of 10%, so it covers the whole rotation of the asteroid at 36-degree intervals. The next one gives you, it's effectively half rotation at 18-degree steps. Third one is 7-degree steps, and the fourth one is 3.5-degree steps. This is to allow you to find the right orientation of the shape model to fit your observations. With an important caveat that you need to understand is you might find more than one orientation fits the observations. In fact, that's probably not going to be uncommon. Then you also have an option to download light curve references and to copy details so that you can paste them into a report or something. Next slide. Here's an illustration of a recent event. And I've plotted here the shape model of the asteroid rotating at 36-degree intervals. The one at the right of the top line corresponds to the nominal time of the event, and it's different orientations on either side of it. Now you can see if you take the middle plot, top and bottom line, that's the asteroid oriented 72 degrees and 90 degrees different from the notional time, but you can see those two shape models look fairly similar. There is the issue of identifying which shape model best fits, or the orientation of the shape model that best fits, does involve some careful fitting, and inherently, an important aspect of this is the reliability of the event times in our recordings. The more I look at the need of what's involved with fitting our observed occultation chords to shape models and distinguishing which one is which one fits best, it is absolutely critical that we have high reliance upon our event times. And this sometimes worries me when we start talking about secondary time systems and so forth, just how reliable our event times are. This is something we're going to have to keep an eye on as we go forward with our camera developments, to make sure that our event times are absolutely precise. It's critical for what we're doing. Next one. Now here's an event which I've been looking at recently. Involves asteroid 107 Camilla, which it's, I think, the 216 July 21st event. It's this is data which hasn't sort of come out generally, but it's stuff that Brad passed on to me the other day. Left-hand column is July 21st. The right-hand column is 2015 August 23rd. The top line is a fit to the chords based on an increase over the published rotation period of the asteroid of 0.000004 hours. That's about 0.01 of a second, I think it is. It's some very small amount, but it's a significant amount. And those two shape models fit the observed chords quite nicely. The bottom line involves a different orientation of the asteroid. It's sort of about 180 degrees rotated. The period has been decreased by 0.00003 hours. And you can see from that the left-hand image, you get quite a good fit. But the right-hand image, it's a good fit for the observations at the left and some of the ones at the right, but not the top two chords at the right. On that basis, option 2 is not the right fit. Option 1 is the right fit. So from that we can deduce, we can increase our precision of knowledge of the rotation of the asteroid Camilla, and we can confirm that this shape model, and there's only one shape model for Camilla, is a valid shape model. Next slide. So going through all the observations of Camilla in the database, 2015, first line should be 2016, July 21st. When you do the fitting, the mean diameter by volume is 221 kilometres, by surface 225 kilometres, 4 kilometre difference. Do the same for the 215 August 23rd event. You get slightly different values, not surprising. Then you start looking at some of the other observations. 2015 May 6, there were three chords in that. The northernmost chord appears to be quite unreliable. Middle chord has a large uncertainty. End result, couldn't determine anything out of it. 2015 February 12, there was, I forget whether there was one or two observers, but it was a double star involved. And so you got the extra parameters, the double star affect the solution, not enough information to resolve anything. 2015 January 1st, one chord with a nearby miss, nothing you can determine out of it. 2014 March 13, three chords of inconsistent length which were close together. That's a case of inadequate timing precision, basically. Couldn't get anything out of it. 2013 May 7, the northernmost chord had severe timing problems reported. The middle chord was flagged as being a possible event, but not a definite event. And again, couldn't get anything out of it. 2011 October 23rd, a single chord observation, which when you did the fit suggested the diameter was at least 218 or 222 kilometres. And 2004 September 5th, observed chords don't fit the shape model or any variation of the shape model. Middle chord was affected by cirrus, so that had to be excluded. I derived the diameters I've given there by assuming the chord durations were correct for the two chords not affected by cloud, and did a notional fit on that, which means that results must be doubtful. So end result is our two recent events with by far the best of that, but a definite result. Next slide. So allocated reduced weight to the 2004 event. We can derive, and this is a little bit crude, the mathematics of it, but the mean diameter of 107 Camilla is 223 plus or minus 4 kilometres. That's probably a generous 4 kilometres. That's on volume, or 227 based on surface area. Now when you look at the satellite values, IRAS quotes 223 plus or minus 17. Our uncertainty is much better than that. The Japanese Acura 200 plus or minus 3.5, that's totally outside of range. WISE gives 219 plus or minus 6, which looks good, except when you talk to the WISE people, what they refer to as, hey, that's the formal uncertainty of the measurement, but overlying all that, there's a 10% systematic uncertainty in their measurements. So it's 219 plus or minus 5.9 plus or minus 22. And we've got 223 plus or minus 4. Next slide. So there's learning to be had out of this. We're almost at the end of this. The first one, and an issue I can't emphasise enough, accurate time base is absolutely essential for this shape model fitting. If you've got uncertainty in the chords, or if you have observed chords which are displaced by 0.3 of a second, that could distort the fitting to the shape model and finish up significantly affecting the diameter determination. can't overemphasize the importance of accurate time base. Second thing is we need to consider the possibility of a shape model fit at 2 or more different orientations. We showed you examples there. As far as I can see, we need to have at least 2 well-observed events to resolve the model and the period correction. And we need to consider in all of this the possibility of the rotation being an error by more than 1 full rotation when we're doing this fitting. Next slide, which is the next but last. The correct model and period should fit all past observations. If you've got reliable old observations, the shape model should fit everything. It's because the shape of the asteroid's not changing itself. So that's the critical part of the fitting process. However, where a fit does not occur, you need to look carefully at the individual observations of past observations. And dare I say it, sometimes you have to have a look at it with a somewhat cynical view of various issues that can surface. And interestingly, shape model fitting, if done correctly, will identify and exclude erroneous chords, which is an issue which, if you're trying to derive asteroid diameters from a statistical treatment of our occultation chord lengths, you don't have an easy means of excluding erroneous chords, but they undoubtedly exist in our data. I would hesitate to put a number on how many occultation chords I think are significantly in error, but I would hazard a guess that it's almost certainly greater than 1%, but probably not much greater than 1%, but they're definitely there. And the last slide is a non-slide. That's my presentation. I'm happy to take questions. Okay. I'll come back. 10 blank. I'm not sure whether. Oh, there's a question here. How does DAMIT handle tumbling asteroids where the axis of rotation is varying? At the moment, neither DAMIT nor ISAM handle tumbling asteroids, but that's coming. And beyond that, I don't know. An interesting thing, but I don't know that the tumbling asteroids is an issue for the type of asteroids we're currently observing. Post-Gaia, that could well be a very different issue. Tony George has said, I understand why we have used mean diameter, but with shape models it should be possible to solve for the ellipsoid. For asteroids like Cleopatra, the mean diameter doesn't mean much. I agree. I guess the main thing that we are doing is any shape model which is available on a system has a scale. The DAMIT system, they have a line which is represented as the mean diameter based on our volume equivalence. that however you define that issue, what we can do with that fitting the occultation results to the shape model is we are putting a kilometre scale on the shape models, and that's not something which can be done with shape models. Shape models provide a shape but not a scale. Our occultation results provide the scale, and it's how you how you express that scale. You could equivalently say the maximum chord across the asteroid, the maximum distance between 2 points on the asteroid is X kilometres. That would be another way of representing the scale. There are many ways of putting the scale there. Traditionally, people talk about the mean diameter of an asteroid. If we're going to use mean diameters, we've got to be careful about what the mean diameter is. But ultimately, what we're doing is providing a scale for the shape models. Now, John Broughton's asked the question, will Gaia produce shape models? My understanding, no. They won't be doing the photometry over a long enough, continuous enough period to get the photometry to do a shape model. So I think the shape models will continue to be generated primarily by amateur photometrists. Tony George says, well explained. So once we set the scale of the shape model, maybe we can then encourage them to publish the ellipsoid parameters for us. For our occultation predictions, this is taking us to another step. Once we have Gaia and we're in a position of generating occultation path predictions with a precision of a couple of kilometres or better, then we have some interesting issues of factoring in the orientation of the asteroid at the time of the occultation event so that we can predict the actual limits of the path as it crosses across the Earth. In that context, we would need to have some sort of ellipsoidal shape model with rotations so that we can predict the precise orientation of the asteroid and factor that into our predictions so that we can accurately position our observers across the path. This is an opportunity for me to point in another issue about Gaia. Gaia is going to be measuring star positions down to about 10 microarc seconds. For the brighter stars, it's less than that for the fainter stars. It will also get positions of asteroids to that type of precision. Now, 1 milliarc second is 2 kilometres, so 10 microarc seconds should be 20 metres. Will we be able to predict the position of an occultation path at the 20 metre type accuracy level? That would be interesting. This is where I find it gets interesting about the accuracy of Gaia. With the asteroids, the biggest source of uncertainty in the asteroid's ephemeris and position is in fact the position, knowing the position of Gaia relative to the Earth at the time of each of its observations. And the basic position is Gaia in its orbit about the L2 Lagrange point they know its position to about 1 kilometre, and that position is the limiting fact, the limiting element on the accuracy we can expect in the long term asteroid lock and path locations. However, they've been doing astrometry on a regular basis of the Gaia satellite, and apparently reduced the effective uncertainty in the position, knowing the position of Gaia, to the small fraction of a second of arc. But in fact, our greatest limitation in being able to predict the location of an occultation path of an asteroid is going to be based on the uncertainty in the location of the Gaia spacecraft when it made its observations. Now, next question. Bob Sandys asked, how much rotation can be expected to occur during the time that a shadow passes from, say, east to west coast of the USA? This is yet another problem that we're going to have to deal with in years to come. For a typical main belt asteroid, the rotation period is sort of 10 to 14 hours. So 10 to 14 hours, 1 hour rotate 36 degrees. Its rotation over a 20-minute period will be about 10 degrees. And that's the sort of time period you're looking at going from east to west coasts of the states. You get some asteroids, and within the realm that we observe, where the rotation period is down around 3 or 4 hours. In the world we're moving into, combining our observations with shape models, we will at some point need to factor in the rotation of the asteroid between the time of the events from different observers. An interesting challenge. Deal with that in a few years' time. Now, Brad's commented, thinks a variable specific for each asteroid, yes. Okay,